Okay. So we're still talking about basic chemistry, and today we're actually also going to move into organic chemistry. We're going to talk a little bit about the biological molecules that make up our body. But before we do that, I want to talk about the properties of water that make it a really important molecule to living systems. And you'll remember from our previous lecture that I mentioned that water molecules within a water molecule, they have covalent bonds. So anytime you see a solid line, this means that there is sharing of electrons. But notice that these water molecules are also connected via hydrogen bonds. And so hydrogen bonds are always designated by a dotted line, and they're relatively weak. So we can put energy into water, break those hydrogen bonds, and the water molecule will evaporate and go into the atmosphere. Now, the thing about these hydrogen bonds is that they're not broken very easily, which explains a lot of the properties that we see associated with water. So the first property I want to talk about is that they have a high heat of vaporization. So water evaporates, it goes from a liquid and turns into a gas, but it takes a lot of energy to do that, right? This is important for a variety of reasons. One is that it means that water will stay in its liquid form on our planet, right? It's not just going to all evaporate when the temperatures get high. And the other thing, it means that it can absorb heat. So for example, we sweat in order to get rid of heat. So if I sweat, then what's going to happen is that energy that is on the surface of my skin, because I get hot and blood rushes through my surface of my skin and my skin turns red, that heat that's being sent to the skin is going to be lost as that energy is transferred into the water molecules, and things are going to evaporate off of me. So if you've ever been in the southern United States or the eastern United States during the summer, you know that it is very muggy, which means that there's lots of humidity, and sweat does not help, right? So you can be like, you'll get out of the shower and there's so much water in the air that you'll immediately be wet, and you will stay wet all day, right? And you're not losing heat because there simply is so much water in the atmosphere that you're not evaporating very quickly, so you're not losing heat as well. The problem is that when you're in deserts, for example, you will actually lose water quite readily, and you might become dehydrated. We also lose a lot of water across our respiratory surface, our lungs, when we breathe out. And so, for example, you might notice that in the winter, when you're sleeping at night, and specifically if you have a wood stove or dry heat, that you might wake up in the middle of the night and be so thirsty. And that's because you have actually gotten rid of water as it has evaporated off the surface of your lungs. And so that can be very drying to the body, right? So high heat of vaporization is due to those hydrogen bonds between the water molecules. Okay. The other characteristic of it is that it is less dense as a solid than a liquid. This is kind of unusual, and it also has to do with the hydrogen bonds. They kind of crystallize, and there's lots of space in ice. You know that ice takes up more space because if you leave a soda pop in the freezer, it will rupture the can, right? Because as it freezes, it actually expands and it becomes less dense. And so this means that ice floats, right? And this is really important from an ecological point of view, because this means that when the water starts to freeze on the river or in the pond, it's going to float to the surface, and then it is actually going to insulate the water below it. And so this means that rivers and streams oftentimes do not freeze solid because the ice insulates And it would be different if the ice formed at the bottom and it would freeze solid and there would be nothing keeping it, right? So this actually means that bodies of water on our planet don't always freeze solid. Sometimes they do, but in many cases they don't, right? Ponds and lakes might get a good layer of ice that is on the surface, but there's water below. Okay. Oops, 3. So water is what we refer to as the universal solvent in biological systems. So almost everything in our body is soluble in water, except for fats, and we'll talk about why. And this is because the water molecule is a polar molecule. And you'll remember that that means that its charge is not equally distributed. So if we drew a water molecule, it would have a negative here and a positive here, right? So it is a polar molecule. So what's going to happen when we put substances in water is that they are going to be pulled apart by this difference in charge. So water molecules are going to adhere to them, and then they're going to go into solution. So for example, if we look at salt, right, where this is a positive and this is a negative, there's going to be an attraction between the oxygen and the sodium, and it's going to pull it into solution. So it's going to ionize it, and it's going to become an electrolyte. So any molecule that has polarity will tend to go into solution. So it will tend to be soluble in water. Okay, the polar molecules are soluble in water. So when we look at these solutions, like a salt solution, it is made up of solutes plus a solvent. Okay. So the solutes in this case would be sodium and chloride that are going to go into solution. So if we sprinkle salt into a beaker of water, the water molecules are actually moving around and they're bumping into each other. And pretty soon what's going to happen is that you're going to not have salt crystals. It's going to dissolve. And then if you let it stand long enough, it's going to go into an equilibrium, which means that it is at an equal concentration throughout the beaker. And so that is actually something that is interesting and that happens even in a non-living system, is things will tend to diffuse from a higher concentration to a lower concentration until an equilibrium is reached. So you would have eventually a glass of salt water that has equal concentration of salt throughout. So the solvent is whatever brings the substances into solution. Okay. So those are like the 3 major characteristics and properties of water that are important. Oh, sorry, I wanted to mention one more. Okay, they have adhesion and cohesion. So adhesion is where they tend to adhere to something, right? So water, like we learned on the filter papers that we used in lab last week, if you put a drop of water on the filter paper, it will move, right? So it will spread out and it will be absorbed across the surface. And that's because the water molecules are adhering and they're cohesive, so they're pulling each other along. So they adhere to the filter paper and then they pull each other along. And this is actually really important in a couple of ways. One way we actually talked about, which has to do with transpiration in plants. So this is the movement of water in plants. So water evaporates off the surface of the leaves. Okay, this pulls on water in the plant. And water is automatically drawn up through the roots. Right? So plants do not use energy to pump water through their body. Right? They're just automatically drawing water up. As it evaporates off the leaves, because of the adhesive and cohesive properties of the water molecule, it just kind of tugs at all the other water molecules, and then it forms a column that just comes up. Okay? So that's transpiration. We have a little bit of this in our body, and in our bodies, in animals, we call it capillary action. So this is in very small vessels, like capillaries. Water is just simply pulled along, and blood, because blood has water as its solvent, is pulled along through the action of these hydrogen bonds between water and the other molecules, the water molecules, and the surface of the capillary. Okay. So movement of fluid through small vessels. Okay, so that's the 4 major ones. Oops. So in your book, touchy. Okay, so in your book, they show this in sodium and chloride, where they're drawn apart by water molecules and into solution. And so you can see here that more than one molecule is actually attracted to each of these ions and draws it into solution. So this is how sodium and chloride are transported in our body, in our tissues, in our blood, right? We have sodium and chloride. Salt solution. All of our cells are surrounded by water that have sodium and chloride in them, kind of like a little mini ocean surrounding each of our cells. Okay, so another important thing that relates to water is the idea of acids and bases in chemistry and in biology. When we look at water, water actually exists in 2 different states. So water is said to dissociate into hydrogen ion. So this would be a hydrogen ion plus a hydroxyl ion. And the reason why I drew the arrow going both directions is actually water goes back and forth between these 2 forms. So when we measure a solution and we're looking at its pH, pH is a measure of the concentration of hydrogen ions in solution. So water is said to be neutral, and there is a scale that goes from 0 to 14. There's no units on this scale, but water is neutral at 7. This is pure water. So pure water means distilled water. So all the chlorine has been taken out of it. It's not like tap water that has minerals and chlorine in it. It's distilled water because that's all it is water. So pure water has a pH of 7. Now the weird thing about the pH scale that you have to remember is that it is kind of opposite of what you would think, because the lower the pH scale, the higher the hydrogen ion concentration. And this is because the pH scale is actually a negative log arithmetic form, and so I can give you an example of how that would work, okay? So if I have my pH value, and then I'm going to put just in a little table, concentration of hydrogen ions. Okay. So if I say my pH value is a 1, the concentration is 1 times 10 to the negative 1. So that number, if I were to write it out, this is my scientific format. If I was to write this out, it would be, this is 1, and because it's a negative, I would take it back a decimal place. So this actually equals 0.01. Right? I went back 2, sorry. So if I go back 1, it's 0.1. That's right. 0.1. There we go. Okay. So actually, that is very acidic. That is a high concentration of hydrogen ions in solution. So if I did 4, it would be 1 times 10 to the negative 4th. And so I take my 1 and I go back 1, 2, 3, 4. So that's 0.0001. So this is 0.0001. So notice how my concentration of hydrogen ions is a power of 10, actually more than 10 with 1,000, lower than it is here. So that's why it is the inverse. The higher the pH, the lower the concentration of hydrogen ions. So if we look at some examples of acids that we have in our body, one good example is HCl, which is hydrochloric acid. Does anybody know where you have HCl in your body? In your stomach, right? So you have, this is the type of acid that your stomach, your gastric juice is made of, hydrochloric acid. And so it actually produces hydrogen ions, right? So sometimes if you have really bad acid heartburn, then you take a proton pump inhibitor, which is actually a proton is a hydrogen ion. So that inhibits the production of hydrogen ions. So that decreases that increases the pH of your stomach and actually makes it neutral, which is a good thing if you have heartburn, but a bad thing if you need to digest protein and if you have that bad bacteria in your gut. Okay. So if we look at how this works, HCl dissociates in water into hydrogen ions plus chloride ions. It's a very strong acid. Now, this is an example of an acid. So what acids do by definition is that they add hydrogen ions to solution, right? So they contribute hydrogen ions to solution, to the solution. We'll put to the solution. Now, the opposite of the acid would be a base, and a base removes hydrogen ions from solution. So an example of a base that you have in your house is, probably have in your house, is baking soda. So baking soda is a form of sodium hydroxide. So this is sodium hydroxide. Baking soda. And when you put this into water, it dissociates into sodium plus a hydroxyl group. So what is going to happen is this hydroxyl group is going to remove, so let's say you have heartburn and you have no Tums or Rolaids or Maalox or anything like that in your house. So one thing that you can possibly do is you go to your kitchen and you make up a glass of baking soda water. Okay, so I'm going to have some baking soda water. I have acid reflux. Okay. So what's going to happen when you mix those two is that we're going to have the formation of water, so that the baking soda, the base, is going to remove the hydrogen ions from solution. And this is going to produce water. So this is going to produce water. So I have just neutralized the acid by adding baking soda. Now, the reason why you do not want to use baking soda on a regular basis is because this is salt, right? So it tastes salty, baking soda does. And salt actually can do lots of damage to your stomach. It can get across the mucous membrane of your stomach and cause bleeding. So it could give you a gastric ulcer because it'll cause your stomach to bleed. And also sodium at high levels is not good for your blood pressure because it will require you to take in more water to dilute the sodium in your blood, so that that is going to increase the pressure. So that's why you take things like Tums, which has calcium instead of sodium. And so the idea is that everybody can use a little extra calcium to help with building of their bones, for example. And it's not going to be bad like sodium hydroxide. So we're going to play with pH and acids and bases and what they do to how you measure them, and then what also they do to biological systems. Okay, so I wanted to mention how this relates, how pH relates to oceans, because you may have heard that with climate change, not only do we see that there's a warming of the oceans, but there's also what is referred to as ocean acidification. So this is because oceans are really good at absorbing carbon dioxide. So carbon dioxide, and this is from the atmosphere, automatically goes into solution in water. That's actually how we breathe it out. It's in solution in our blood. But it's in solution, or excuse me, it's in the air, and then the water absorbs it. But the problem with CO2 in the water is that it combines with water and it produces a weak acid called carbonic acid. So this is carbonic acid. And this carbonic acid then dissociates, and this means that it goes back and forth, so it's kind of weak, into hydrogen ions plus carbonic ions. So you just need to know the hydrogen ions here. So this would be a negative. So one of the problems that we have is that there's a lot more carbon dioxide in our atmosphere than there was previously. Right? Because we're burning fossil fuels, we're releasing CO2 in the atmosphere, and we thought it was actually a good thing that the oceans were absorbing it. Because the hope was that the oceans would absorb it and maybe produce algae or other things, and then they would take it out of the atmosphere and it would become less of a greenhouse gas. But the problem is that we're seeing that we're actually seeing a slight acidification. So if we're talking about the pH of the ocean, it is basic. So it is 8.4 about, right, the pH of the ocean. But it has decreased, or it was, so it is decreasing to about 8.1. And you're like, well, 8, that does not mean it's an acid, right? That means that it's a base because it's above 7. And so, but it's becoming more acidic because it's going towards 7, towards acidity. And so that's why they call it ocean acidification. Does anybody know what this is causing in particular? Things that would be bad about?
Shark attacks. Shark attacks?
No, not shark attacks. What kinds of things are dissolved by acid in the ocean? Anybody know? Reefs, for example. So organisms that have calcium carbonate shells. Right? So this would be like oysters, right? Clams, even like the nautilus, which is related to an octopus, but also coral reefs. Okay. So these organisms are starting to see that their shells, you're starting to be able to actually measure that their shells are dissolving in this acidic ocean, and they're becoming weaker, right? And they're less able to deposit their calcium and create shells. And so even off the coast of the Pacific Ocean, off the coast of Oregon, some of the oyster farms off the coast of Oregon are having a hard time producing baby oysters because of the pH of the water. So that is a kind of a hidden effect of climate change that's related to climate change, but it's not due to warming, but actually it's due to acidification. Okay, so we're going to go into organic chemistry. So whereas before that was just kind of basic chemistry, inorganic. So this would be versus inorganic. Water is actually an inorganic molecule. So is salt, would be inorganic. Hydrogen chloride, inorganic. Sodium hydroxide, all of those are inorganic. So when we look at what organic molecules are by definition, they tend to have long chains, or they have carbon. So I'll just put they have carbon. Okay. Tend to So they tend to have long chains of carbon atoms. This one doesn't. This is a very simple organic molecule, but it still has carbon. It's actually said to be a hydrocarbon because that's all it has is a hydrogen groups or hydrogen atoms and carbon. So this is actually a source of fuel. You can actually burn methane, right? We talked about that because it's being released from the permafrost. You can actually burn it and use it as a source of heat. So this is some examples of the structure. So when we look at all of these carbon atoms, you see that they are covalently bonded to one another. So it has to do with the sharing of electrons. You'll also see that sometimes these chains form rings. And so some molecules that are ring-shaped include glucose. So glucose is not a straight chain of carbon, but it is actually a ring. So we have carbon rings. Okay, so carbon rings. So example would be glucose. And when you look at chemical or organic molecules, oftentimes they use a shorthand where they'll actually eliminate the carbons. And so you'll actually see something that looks like this in your book. Oops, maybe not. Oh, sorry. It'll look like this. O, and then it'll be a C. Probably have this on the next picture, on the next page. It looks something like this. Okay. I look like this. Okay. So sometimes you see them where they actually remove the carbon, right? So this is organic chemistry shorthand. So they've actually also removed all of the molecules that are covalently attached to the carbon, and they just show them as a simplified ring structure. But that, even though, don't be confused, this still would have the carbons in them. They're just making it more simple to draw. Okay. Okay. So the first group of organic molecules that we're going to talk about are the carbohydrates. So when you look at that, that has to do with, we just talked about carbon and hydrogen, right? So the carbohydrates have generally just a lot of carbon covalently bonded to the hydrogen. Now, these are also called the saccharides. And when you think about saccharide, if you say somebody is saccharin, what do you think of? You say that person is so saccharin. You ever heard that word before? No, that means that they are sweet, right? So saccharides, saccharin means sweet, right? Carbohydrates. So we can have molecules that are monosaccharides. Okay. So the monosaccharides mean they have one ring of carbon molecules, of carbon atoms, one ring, one structure, right? And so this would be like glucose, also fructose. Okay. Fructose sugar is what's commonly found in fruit. Okay. Those are actually the subunits that make up larger structures. So we can then talk about disaccharides. So think 2. So for example, sucrose, which is your table sugar, is made up of glucose plus fructose. Yes, I'll show you a picture of it. I think I probably have a picture in the next one. Okay, so glucose and fructose. Okay, so those would be monosaccharides. We can put them together, and this is another example of one. Maltose would be a disaccharide. And so malt is what is produced by grains when they ferment, when they start to break down and produce sugars. So that would be what we use to produce like beer. You would add malt, maltose, to the yeast so that that would give them energy to produce alcohol. Okay? So that is a disaccharide. We also have structures called polysaccharides. So this means that there are many, many monosaccharides covalently bonded. So not just 2, but generally like hundreds, if not thousands, right? So the polysaccharide carbohydrate that we use is called glycogen. So what this is many glucose molecules covalently bonded. So when we take in, say we take in a candy bar, right? Our blood sugar level goes up. So our glucose in our blood is elevated temporarily. We want our body to be able to remove that glucose and store it, right? So what hormone is important in removing glucose so that we can store it? Anybody know? What is that hormone that does that? Insulin, right? So I eat a candy bar and drink a Mountain Dew. My glucose levels are high, right? I can measure them, right? Then pretty soon my glucose levels go down. And so the question is, where did that glucose go? The glucose was stored as glycogen. And so this is the storage of glucose in the liver and in the muscle. Right? So if I then don't eat anything all day, I still need glucose because that's the energy that my brain runs on. My nervous system needs a steady supply of glucose. So then I break it down slowly over time, and it's released back into circulation. Okay, so glycogen is really important for that. Now, there is another polysaccharide that is found in plants that you probably have heard of, and it is cellulose. Cellulose is made up, just like glycogen, of glucose. Cellulose, however, in plants is used for their structure, right? So it's used in plant cell walls. So unlike us, animals, plants actually have walls around their cells, and that's their structural support. So this is what is said to be a structural polysaccharide. In our diet, we have a name for this. And what would it be? Like how much in your diet do you get of this? What is that called? Fiber. Fiber, right? So this is our fiber. So we actually do not have the enzymes to break down cellulose to use it as energy, which is actually kind of a good thing because we tend to be, we have too much energy, most of us, because we're depositing it as fat, right? But you can think about all the plants, all the cellulose that is out there, and wouldn't it be interesting if some organisms could use cellulose as fuel, right, as energy? And that is actually where we have ruminants. Okay, so ruminants are the only organisms that can, or only animals that can use, actually termites can do this too, so maybe I can't say only, but ruminants are animals that can actually use cellulose. And so when we think about ruminants, we think about cows, sheep, goats, camels, okay? So those are, horses are not ruminants. Deer are not ruminants. Okay, they have another mechanism which allows them to eat plants. But all of these organisms have in their gut a special chamber called a rumen. So what do ruminants have in their rumen that allows them to digest cellulose? What do they have that we do not? We don't have a rumen. We don't have a big fermentation chamber, but they have what in their fermentation chamber? They actually have 4 chambers to their stomach. What do they have to have in their digestive tract to be able to break down cellulose? What does fermentation mean? When you think about things for bacteria, okay? So they have symbiotic bacteria that break down cellulose. So what happens is that these bacteria use cellulose as energy, and then the bacteria reproduce, and then the ruminants regurgitate their food and chew it. So they ruminate on it, right? So that's when cows and sheep and goats are laying around and they're just chewing their cud, right? And then they swallow it again, and then that fermented mass of vegetation with its bacteria is then digested, and the nutrients are taken up. So the symbiotic bacteria are able to break down the cellulose and use it. So if we look at just a quick image of the cow's stomach. Okay. So this is my fermentation chamber. It's a huge part of the stomach right here. And so they first swallow it. This is where fermentation, the bacteria break down the cellulose, reproduce, and then they regurgitate it, they chew it some more, and then it goes into the other parts of the stomach that actually release enzymes to break down the chewed mass of food and then absorb the nutrients in the intestine. So ruminants actually have a 4-chambered stomach. As I mentioned before, termites also have symbiotic organisms that are actually allow them to digest the cellulose in wood. They actually cannot digest it. Termites are animals, so they have these microorganisms in their gut that helps to digest the cellulose. The interesting thing about cellulose and glycogen is they're very similar in their structure. So glycogen, notice how the cellulose is, these are rings, these are carbon rings. So this would be like glucose, each one of those. We have another polysaccharide that is used by plants. We do not store glucose as starch, but plants do. So we can put starch down underneath your polysaccharides. So starch is a plant polysaccharide that is used to store energy. So plants like potatoes take the energy that they get from photosynthesis and they store it in their roots, and they form what are called tubers. And so their roots get big, full of starch, and they might even be able to overwinter. And so if you don't pick all your potatoes, which sometimes happens if they don't freeze, is that the next year they'll actually use the starch that they stored in their tubers, and then they'll actually grow from that. So they'll germinate. Sometimes your potatoes germinate in your house, right? You put them in a cupboard, right? They start to produce leaves and stems and that kind of stuff. So that's the starch. So starch is glucose. Okay, so the next major group of organic molecules is what we call lipids. And lipids are characterized by not soluble or not being soluble in water. So would you say that they are polar or nonpolar? Nonpolar. So they also have a name, and that is that they are hydrophobic. So we can also say that they are hydrophobic versus hydrophilic. So these are nonpolar, polar, and they are hydrophobic versus hydrophilic. So that means that they're water-fearing, so they're repelled by water. So this is like when you put oil in water and they form big globules, right? They don't disperse. They actually are attracted to, or they're not attracted to each other, but they're repelled by the water, and so they tend to come together. The type of lipids that we store in our body for energy are what are referred to as triglycerides. And just like the name suggests, they have three of something. So they have 3 fatty acids attached to a glycerol molecule. Right. So the triglycerides are stored in our fat cells. The fat cells could either be subcutaneous, so that fat can be underneath our skin, but in some cases, fat is also inside the body cavity around organs. And so that is called visceral fat. And so which is worse to have from a point of view of cardiovascular disease? Subcutaneous fat or visceral fat? Visceral fat. So visceral fat, sometimes you see guys or even women that have big bellies, but it's hard, right? And that means that they probably have lots of fat underneath their muscle, which is that would be around their organs, which tends to have a higher link to cardiovascular disease like heart attacks, for example. Okay, so they're stored in the fat tissue. They're actually broken down by the liver. And when the liver breaks them down, sometimes there's a byproduct. And this byproduct is the name of popular diet these days. So what do they produce that is a byproduct? Ketone, right? So they produce ketone bodies. So you probably have heard of the ketogenic diet. Okay. And so this is this idea that you want to be in fat burning mode, because fat is only burned after you have used up all of your glycogen. So first the body uses glucose and glycogen, and then you have to get to the point where you've used all that, and then you'll start to burn fat. We can also use protein for energy, but we don't generally want to do that because that means that you're using muscle and other structural things to produce energy, and that's a bad thing. So the ketogenic diet just means that you've gotten to the point where you've used up all your glucose and you're starting to burn fat, right? So the idea is that it's low carbohydrate, and a lot of people promote fasting, right? So you only eat 8 hours a day and diet for 16, don't eat anything for 16 hours a day. And that gets you in a ketogenic state, right? So fasting would be that. Okay. So we actually have different types of triglycerides. So we have what are called saturated fats. So saturated fats means that there are the maximum number of hydrogen ions attached to the carbon chain, right? So this could go on and the fatty acids tend to be really long. But saturated means that they're saturated with hydrogen atoms, right? As this is opposed to unsaturated. So if I was to draw my unsaturated one here, I might have a double bond here, and then my hydrogen. Okay. So this is unsaturated. So what that means is that because of this double bond, there's not the maximum number of hydrogen atoms involved in the molecule. So saturated has to do with the amount of hydrogen. Okay. So which one of these tends to be a liquid and which one tends to be a solid at room temperature? Saturated or unsaturated? So butter is kind of a solid. Is it saturated or unsaturated? It is saturated, right? So this would include animal fat. It would include butter. It also includes, weirdly, coconut oil, because coconut oil tends to be a solid at room temperature. Lard, animal fat. Okay. So unsaturated would be like corn oil, right? So these are my oils, right? Sesame oil. Oops, how do you spell sesame? Sesame oil. So these are the types of triglycerides, saturated and unsaturated, that are found normally, right? However, we have actually taken some of these oils and we've actually caused them to become a solid. So corn oil, for example, can be turned into margarine. And how do they do that? How do they take an oil and turn it into a solid? It's a process that's related to the difference between saturated and unsaturated. You'll see that margarine, you look at a tub of margarine, which there's not a lot of it out there anymore. When I was a child, everybody ate margarine, okay? This is hydrogenated corn oil. So I've actually added hydrogen to the corn oil. I've broken those double bonds, and I've actually turned it into a solid. So hydrogenation just means that you've added hydrogen atoms. This, however, also relates to something that has been big in kind of nutrition health. And this is related to that when you hydrogenate corn oil, this produces a trans fat. So the trans fat has to do with the orientation of the hydrogen related to the carbon, and trans fats is believed to be a major source of cardiovascular disease, like where you get blockages of arteries, right? So this is very bad for your blood vessels, because trans fat causes atherosclerosis, which leads to heart attacks. So that's why they now, it's like trans fat free, right? No trans fat. Governments are thinking about banning the use of trans fat in fast food places, just simply to reduce the amount of money that is used to pay for health bills of people that eat. Be better if they were just not using hydrogenated oils, but straight oils. Okay, so let's look at a diagram or image that shows this, triglycerides. So this is my fatty acids, okay? This is the glycerol molecule. The difference between saturated and unsaturated. Notice my unsaturated has double bonds. And what this means when it has this double bonds is that means that the fatty acids cannot stack closely together. So that means that it's more likely to be a liquid. So when these fatty acids have no double bonds in them, then these stack really nice, and that turns it into a solid. And then the trans fat looks like this. So cis and trans are terminology that's oftentimes used in organic chemistry. Cis just means it's on the same side, and trans means that it's on the opposite side. So this is a cis fat molecule. The trans fat that's produced when you add hydrogen to corn oil makes it so that there's hydrogen on each side, and that's the whole basis for the difference between a good fat and a bad fat has to do with that trans. Okay, so we'll stop there for today. If you have lab today, make sure to come. It appears that we have quite a bit of space in each lab. So if you, again, make sure that you come to either Monday's lab or Wednesday's lab. It's really important that you don't miss lab.